You're listening to AI Podcast. I'm Ryan, and today we're digging into an ICLR 2025 paper called AFlow, Automating Agentic Workflow Generation, led by Jiayi Zhang and Jinyu Xiang. Thanks for joining me, Sophia.
Happy to be here. Give me the quick version first. What's the headline?
The takeaway is simple. The authors treat the design of large language model agentic workflows as a search problem. They represent a workflow as code, then use a search algorithm, specifically Monte Carlo tree search, to automatically edit and improve that code until the workflow performs well on real tasks. In their experiments across 6 standard reasoning benchmarks, the automatically discovered workflows beat strong hand-built ones by roughly 5 to 6% on average. And on some tasks, those workflows let smaller, cheaper models outperform GPT-4o at around 5% of its dollar cost.
That's a clean TLDR. Before we go deeper, who are the people behind this?
Representative authors are Zhang and Jinyu Xiang with a broader team of collaborators. We'll keep it simple and say Zhang and Xiang and colleagues.
Great. Now set the stage. What problem are they solving here?
Agentic workflows are multi-step procedures where an LLM is asked to reason, draft, check, revise, sometimes vote or ensemble results, and occasionally call tools. Today, building those pipelines is largely artisanal. Teams tinker with prompts and wiring, and it's slow, brittle, and hard to transfer to new domains. The gap is a systematic way to generate and improve these workflows without so much human trial and error.
Right. Hand-designed flows can be clever but fragile. Haven't people tried automating parts of this already?
They have. A lot of prior work tunes prompts or hyperparameters inside a fixed flow, which helps but doesn't change the structure. Early systems that do search over workflows often rely on human-seeded designs or explore inefficiently, so gains stall when the search budget is limited. In short, earlier methods either lock you into a fixed shape or need too much human setup to be truly automatic.
So what's different about AFlow?
AFlow treats the workflow like a program you can edit. Each node is an LLM call, and edges define the logic, like who reviews what and when to revise. The system keeps a pool of candidate programs and uses Monte Carlo tree search to decide which one to expand next. An optimizer LLM proposes code edits, such as adding a review step or adjusting prompts and connections. Then the edited workflow is executed on a small validation set. The observed score is fed back into the search, so it spends more time in promising regions.
So the optimizer LLM writes and rewrites the workflow code, and a separate executor model actually runs the tasks inside each candidate workflow, right?
Exactly. To speed exploration, AFlow also includes reusable building blocks the authors call operators, like generate, review, revise, ensemble, and test. These don't force a particular structure, but they give the search higher-level moves that are often useful.
I like the recipe analogy. The optimizer is the chef trying variations, and the executor is the kitchen cooking the dish. How did they test it?
They evaluated across 6 well-known benchmarks spanning code, math, and question answering. For coding, they used Human Evil and MBPP. For math reasoning, GSM-8K and Math. For reading and multi-hop reasoning over text, Hotpot QA and Drop. They compared against strong manual workflows like chain of thought with self-consistency or debate-style setups, as well as prior automated workflow methods. They also track token costs to report cost effectiveness, not just accuracy. The search runs for multiple rounds until performance plateaus.
And the results?
The pattern is consistent. Automatically discovered workflows edge out handcrafted ones on average across the 6 tasks. The average gain is around 5 to 6%, with larger jumps on some of the harder subsets. A practical highlight is cost. AFlow found workflows let smaller, cheaper models match or beat GPT-4o on certain tasks while spending only a small fraction of the money, about 5% in the reported comparisons.
That cost angle is compelling. What about portability? If a workflow is tuned with one model, does it still work if you swap the model?
They report that workflows usually transfer reasonably well, but there are model-specific preferences. In plain terms, each model has quirks, so a workflow discovered with one model can work on another, just not always as well as a workflow discovered directly for that other model.
All right, let's put on the skeptic hat. What should listeners watch out for?
First, reproducibility. Several experiments rely on proprietary API models as the optimizer or as executors, which introduces version drift and rate limits. Second, search budgets matter. The space is huge, so different seeds or budgets can lead to different best workflows. Third, priors. Those operator templates are helpful but remain human-designed priors that bias exploration, which is pragmatic but not fully hands-off. And finally, coverage. The benchmarks are strong signals, but they don't cover open-ended tool use or complex retrieval pipelines where evaluation is trickier.
That makes sense. Did they share anything to help others reproduce the work?
Yes, the framework is open source, and they provide artifacts so others can rerun evaluations and inspect how workflows evolve during search. That's helpful for transparency.
Zoom in for a moment. Monte Carlo tree search can sound abstract. How would you explain its role here to a non-researcher?
Imagine a branching maze where each junction is an edit to the workflow. You can't explore every path. MCTS balances exploration and exploitation. It tries new edits to see if they're promising, and it also doubles down on edits that paid off before. Each tested workflow gets a score, and that feedback updates the map so the search gravitates toward productive regions and away from dead ends.
Got it. If you were an engineering lead, how would you use this?
Two main ways. First, for a new task where you don't have a good pipeline, let AFlow search on a small validation set to propose a solid starting workflow without weeks of manual tweaking. Second, for cost optimization. If you need to reduce inference spend, search for workflows that help a smaller model close the gap with a larger one, then check whether the quality-cost trade-off is acceptable for your use case.
And for researchers, what future directions feel promising?
Broader search strategies that mix MCTS with evolutionary ideas. Co-searching not just the workflow shape, but which model runs each node to get the best price-performance mix. Learning operators from high-performing workflows instead of handcrafting them, and extending to tool use, retrieval-augmented generation, and multimodal tasks where judging quality is harder and good workflows matter even more.
Any parting caveats you'd underline?
Keep evaluation hygiene front and center. Fix seeds, publish stable validation and test splits. Report variance, not just averages, and make cost comparisons apples to apples since pricing and defaults change. The paper is careful about many of these, and as more teams adopt this approach, those standards will matter even more.
Wrap it up for us.
AFlow is a thoughtful step toward turning workflow design from an art project into an engineering process. By searching over code-represented workflows and letting an LLM propose edits, it finds pipelines that perform well and often save money. It's not the last word, but it's a credible blueprint for automating what many teams still do by hand.
Clear and helpful. Thanks, Ryan, and thanks to everyone listening. This has been AI Podcast. If you found this useful, share it with a colleague, and we'll see you next time.